This talk is titled Cipherspaces and Darknets, an overview of attack strategies. A little bit about me. My name is Adrian Crenshaw and I run IronGeek.com. I have an interest in InfoSec education. I don't know everything. I'm just a geek with time on my hands, so if I get something wrong, please let me know. I'd be interested in knowing the truth. I'm also an irregular on the ISD podcast. We put out podcasts 5 times a week. I'm usually on Thursdays. And I'm also a researcher for the Tenacity Institute, which was kind enough to help me get out here to DEF CON this year. Just a little bit of background you should probably know before we continue on with this talk. What do I mean when I say Darknet? Well, there's a few different definitions out there, but the one I'm looking from for this presentation is essentially anonymizing networks. There's many ways these are constructed, but generally they involve encryption and multiple proxies, or hops, where essentially you send the message in encrypted. You may have multiple levels of encryption so that each person you pass it through can only see their level of encryption, but it's still encrypted when they pass it on to the next hop. And the idea of these multiple proxies or hops, these nodes, is to make it confusing for an adversary to figure out who initially sent the message in to the network to begin with. This is commonly referred to as a mixed net or a mixed cascade, depending on how things are connected. They're sometimes also referred to as Cipherspaces, and I really like this term. Darknets can be a little bit more confusing because sometimes when people say Darknets, they mean a truly private network where it's invite only, and an open net would be sort of like a Cipherspace where anybody can join in, kind of like Tor and I2P are by default. So the terminology can get a little confusing, but I mean Darknets in the broader sense. Tor and I2P would be my main reference examples for this presentation, though there are a lot of other ones out there. And keep in mind when I'm showing off various common attack techniques, Tor and I2P both have mitigations for a lot of these. However, they're good example frameworks to use when trying to explain these concepts. Some extra notes. Things get kind of subtle when you start talking about darknets. Terms vary from researcher to researcher. What one person uses to refer to a particular attack, someone else may use slightly different terminology. Many weaknesses are interrelated. For instance, rogue peers or Sybil attacks can be used to help with traffic correlation attacks. Also, there's a lot of other anonymizing networks out there besides just Tor and I2P. To name a few, the list you see in front of you right now: MorphMix, Tarzan, MixMinion, MixMaster, Jap, Mute, Ant P2P, Haystack, and so forth. The focus of this talk, however, and the illustrations I'll be using, are more geared around using Tor and I2P as models. I'm also going to try to keep it a little bit more real world versus academic. A lot of the attacks shown are phrased in very academic terms and may not be as easy to follow unless you've read a lot of other papers in the same field. So I'm going to try to make this accessible to people who are just getting around and learning in darknets like Tor and I2P. When it comes to darknets, your threat model and adversaries matter a whole lot. You can't protect against everything. A lot of people try to force general internet protocols across these darknets, and while the darknet itself may be well designed as far as anonymity is concerned, the protocol routing on top of it may not be. Some protocols like Bittorrent are sort of a lost cause, but if you're also expecting completely interactive super duper Web 2.0 sorts of interactivity, that may be a lost cause too. You start allowing every single plugin, all JavaScript, Flash, and whatnot, your anonymity is pretty much out the window for reasons I'll be discussing later on in this presentation. Users may do something to reveal themselves, and there's only so much the developers of systems like Tor and I2P can do to protect people from themselves. Some attacks I'll be showing may outright reveal the client or host of a service or who's actually sending data into the network, and some of them just reduce the anonymity set of the person. Basically, you're just weeding it down and getting closer to figuring out who it is. For instance, something like, I know this person is in Germany, or I know this person is a Windows user. Things like that. And they're not outright identification attacks. However, just reducing the anonymity set can be helpful to attackers in some cases. Some attacks I'll be talking about are active, as in the attackers sitting there and actually actively probing boxes and looking for things and causing interaction on the network. And some may be passive. They may be sitting there outside the darknet just sniffing internet traffic and trying to do correlation attacks, which I'll be talking about a little bit later. When it comes to attacking a darknet, it's all location, location, location. Internal versus external. There's certain attacks you can pull off while internal to the darknet, and certain ones that you are external to the darknet when you pull off. For instance, if you're sitting there and you're trying to grab data and look at metadata, you're kind of internal because you have to become part of the darknet and grab data. External attacks could be things as simple as traffic correlation, where you could do it without ever actually becoming a member of the darknet. Adversaries vary by power. What it takes to protect you from one adversary may not work for another. On your high end, you might have things like nation states, especially nations that have greater control of the internet connectivity. For instance, the United States, it's kind of hard to cut every single network connection. However, in some smaller third world countries, not necessarily so difficult. And state-ran adversaries probably have more power as far as looking at your network traffic and being able to figure out who's talking to who. Similar things goes for ISPs. Western democracies versus others, in some cases, depending on who your adversary is, makes a big difference. For instance, in Western democracies, the fact that you're using a darknet probably isn't necessarily going to be a problem for you. They might not be able to see the data that you're sending across, but they know you're using one. However, just the mere fact that you're using it and trying to hide yourself in certain countries is probably going to get someone to come knock at your door. Some governments have more limited resources than others. Even with a very powerful government, they can only check out so many leads. This is another thing where having more nodes in a network becomes very handy, and also bouncing across multiple jurisdictions while someone is sending traffic through the darknet. Someone with an ISP who runs an ISP, or someone with a lot of nodes, can influence traffic and has a greater visibility into the entire network. So this is a pretty powerful adversary. And sometimes this might be working in correlation with a nation state. There's also various private interest groups out there that may be wanting to look into darknets and try to reveal someone's true identity. These would be things like RIA and the MPAA. However, these groups are a little bit more limited as far as what kind of analysis they can do to figure out who's who. And then occasionally you just have some schmuck like me with extra time on his hands. I'm probably one of the more limited adversaries, other than from the standpoint of I have the time and the inclination to go looking around. One of the darknets I'll be talking a lot about is Tor. And probably most of you all are somewhat familiar with the Tor if you're sitting in on this talk. Tor uses layered encryption, where each hop along the way has its own key, and so messages are wrapped in multiple layers, and each hop can only unencrypt its layer and send it on. By doing this, none of the hops along the path until you get to the exit point can see what the data is, and hopefully by the time it gets to the exit point doesn't know who it initially came from. It uses bidirectional tunnels, so basically your in path and your out path should be the same. It also uses a central infrastructure in the form of directory servers, where you can request, okay, give me some Tor routers I can route through. It has other ways of finding routers that aren't inside of the directory, but keep this in mind, Tor has a more centralized infrastructure, which will come into play later on when we talk about some other attacks. Tor is mostly focused on outproxying to the internet so people can surf the public internet anonymously, but it does also have the capability to do hidden services. For more information on it, go check out the Tor project webpage. Another cyberspace I'll be using as a model is I2P. I2P uses directional tunnels. Essentially, your box will have multiple in and out tunnels. It'll send a message out one of its out tunnels and hopefully into someone else's in tunnel, which will eventually get it to its destination. Once it gets there, that destination will send the return message back out one of its out tunnels and hopefully get back to one of your in tunnels. By having these two different directions of communications, the paths aren't all necessarily the same for both the request and the reply, and this confuses some attacks. I2P is also decentralized. It uses a distributed hash table known as NetDB for coordinating communications and what routers are available and who can talk to who and where you can go to reach certain EAP sites or certain services inside the I2P network. I2P, much like Tor, also uses layered encryption, and it's layered throughout the entire thing to where each individual communicator has their own key, but it's also a key along the entire path, which I'll try to illustrate in the next graphic. It's mostly focused on providing anonymous services. If you're familiar with Tor hidden services, I2P has much the same kind of thing, and that's its core focus, at least from the way I look at it. But there are at least a few out proxies to the internet, though generally speaking, when you do the default install, you're using just one. Now here's a basic way of how I2P's encryption layers can be illustrated. You have 3 levels of encryption, basically from hop to hop, from tunnel through tunnel, and from endpoint to endpoint. You can do more research on how I2P does its encryption out on the website. It gets pretty complicated mathematic-wise, and I don't think I'm the most qualified person to discuss it with you. I've created this animation to illustrate some of the conceptual differences between onion routing and garlic routing. Although currently the way I2P implements it, it doesn't use garlic routing quite this way or to its full potential. However, some of these ideas could be used with the message format that I2P has, and maybe in future reimplementations they will be there. But one of the ideas behind garlic routing is you can combine multiple messages together, send them out, and actually have them separate and have different destinations for individual cloves. Doing things like this, eventually you possibly could do things like multicast or cause extra confusion to traffic analysis attacks, because while it might be one message in one location, once it gets to a certain exit point, it can become multiple messages to multiple destinations, and on the way back they may all be taking different paths as well. The first attack I'm going to be talking about is untrusted exit points. This attack I'm using more of the Tor-centric model to discuss it, since I2P, most of the time you're staying internal to the network. You gotta wonder, the exit point that you're sending your traffic out of, is it looking at your data? Traffic may be encrypted while it's inside the network, but it's unencrypted outbound. Now, if you're just worried about anonymity, this really isn't all that big of a problem. However, some people send some traffic through Tor that they really shouldn't. There have been quite a few incidents revolving around malicious exit points. For example, Dan Egerstad and the embassy hack. A whole bunch of embassy workers were afraid of the host country looking at what they were doing on the internet, so they started using Tor to tunnel out. Well, Dan had set up several exit points and was able to monitor the traffic on them. Of course, various people working at the embassy were using plain text protocols like POP3, SMTP, HTTP basic that were passing the credentials and the information in the clear. And he was able to get quite a bit of information that way. Another example is Moxie Marlinspike, who did something similar, but he used SSL strip. Now normally if you're tunneling HTTPS traffic through Tor, you should be fairly good to go. But SSL strip would take that HTTPS connection, drop off the S, and make it just straight up HTTP. If the person on the other end wasn't paying attention and didn't notice that it dropped the connection down, then Moxie could still sniff the connection and see the data. This animation should give you a rough idea of not only how Tor works, but also why an untrusted exit node is such a big problem. When you're using Tor, you have those layers of encryption. So let's say you send a message in as a request. It gets to its first hop, layer gets stripped off, gets to its next hop, layer gets stripped off, and gets sent on. Eventually it goes out the out proxy, unencrypted, barring whatever encryption the protocol itself that's writing inside of Tor supports. At that point, it can either be sniffed or modified and sent back. That modification part is kind of important for some attacks I'll be showing later on, such as embedding content that doesn't necessarily respect the proxy settings of the browser, along with some other oddball attacks. Now, there are several different mitigations you can use against untrusted exit points. First of all, keep in mind that Tor is for anonymity, not necessarily security. Use end-to-end encryption. Don't use protocols that send things in plain text like HTTP basic and FTP unless you tunnel them over something else. Also, keep an eye out for certain attacks that might drop the encryption. For instance, someone using SSL strip to take an SSL encrypted session and turn it back just to HTTP. So you kind of got to keep an eye on what your browser is doing. Also, keep in mind that using plaintext protocols that send your username and email addresses across Tor isn't exactly helping you as far as anonymity, since people are seeing who you are based on those names. Another attack I want to discuss is DNS leaks, along with a few other protocol leaks that are in a similar vein. I'm sort of lumping different things together into this one category. The key feature of this style of attack is that some traffic goes outside of the anonymizing network and doesn't use its proxy. A common example of this is DNS leaks. Badly configured proxy settings could lead to some types of traffic to go elsewhere, outside of the Cipherspace. A snooper can use web bugs then to figure out the location of that particular person. HTTPS is a good example, but plugins can also be an issue if they don't properly respect the proxy settings of the web browser. Application layer stuff is generally going to be a problem, and in my mind, it's probably a bigger issue than the traffic analysis attacks that academia likes to focus on. JavaScript is pretty much just hosed, and it's a great example of application layer stuff screwing people up. Check out Gregory Fleischer's DEF CON 17 talk for more information. The first application level problem I'd like to cover is DNS leaks. If the box isn't set properly to use the proxy for DNS queries, then it may send to an actual DNS server. Now, granted, all the traffic going into the Darknet may be encrypted all the way out to the exit point. However, the DNS server that's receiving these requests may see that a person is going to someplace.com, someplace.onion, someplace.i2p, based solely on the fact that, hey, this box is requesting this name from me, so obviously that must be where they're going, even if I can't see the traffic. There's several mitigations to help protect against DNS leaks. First of all, you should be looking for any kind of DNS requests that are going outside your proxy. What you might want to do is bring up Wireshark or TCP dump and throw in the libpcap filter port 53 and see if any kind of DNS traffic is going out. This should cover you in most cases. Now, for Firefox, you may want to go into About Config and make sure the setting that show up on the screen is set to true so that it knows to send DNS requests through the proxy. However, how you do this from application to application varies a lot. Tor button can also help to make sure things are configured in the right way, and generally speaking, if you're using Tor as a client, use the Tor browser bundle. You're a lot safer that way. As I said before, applications vary from place to place. If you're configuring your IRC client, that's in a different location. If you're configuring SSH to go through a Darknet, that's in another location as well. In some cases, if you want to be really paranoid, the box you're using, firewall off port 53, don't allow it to egress, and that might be a good call. Another option you have with Tor is to configure this in your Tor RC, DNS port 53 and automap hosts on resolve. Then you can take your box and point its DNS server entry to be your local host and do all your resolution locally. And this is probably a good call for certain applications that don't support you telling them to send all DNS queries through the proxy. Another example of an application level oddity that can cause issues is it's grabbing content outside of the Darknet. For instance, let's say a browser is configured badly and it's configured to send all HTTP traffic through the Darknet, but not necessarily HTTPS. I'll illustrate that here. Let's say they send a request and they get back a page, but in that page is an image. That image is requested using HTTPS or possibly some other protocols depending on the browser being used. Where when they request that image, it's going outside the Darknet. Now there's fixes for this as well. This is kind of an issue with your browser being misconfigured, but you might be able to apply the same concept to other applications. In the case of I2P, what I'd screwed up here was I'd set it to only use the HTTP proxy. Another option you could use is say use this proxy for all protocols. That won't necessarily work, but at least it makes it fail when they try to make that connection via HTTPS. Another option might be to actually configure the SSL proxy, although I think last time I checked I2P that it's kind of questionable whether or not this particular proxy that it's using by default for SSL proxying has to do like a connect. I think the last time I checked it wasn't up that particular out proxy, but your mileage may vary. Another example of where application level things can totally ruin anonymity would be in the case of cookies or super cookies as related to plugins like Flash. Let's say someone's web surfing along and they visit a site and they get a cookie from it. However, they're not using something like Tor button that tries to manage state well. So later on they decide, I want to visit that same site again, but I want to be somewhat anonymous, so I'll use Tor at this point. Well, if they still have that valid cookie there, they could very well be passing that cookie along Tor, and well, if the evil server happened to see, oh, okay, he connected to me all over the public internet and he gave me that cookie, now he's connecting to me over Tor and giving me that cookie, it's the same person. So that's something to keep in mind, and that's one of the reasons why the Tor browser bundle is so highly recommended, because it tries to keep these sorts of session state issues in check. Most of the attacks I've been talking about so far have been to reveal the identity of the client. But let's say someone's hosting an EAP site or a Tor hidden service. How would someone go about revealing that? Well, there's also problems with various applications when all that is concerned. Let's say you're running, for an example, a vulnerable web app that has some kind of shell execution vulnerability. If an attacker sends an exploit and payload through that tells your box to, hey, connect back to me over the public internet, it might very well do that, and if you monitor that connection and see it coming back, well, if you see it coming back over the public internet, you've revealed the true network identity of that particular hidden service or EAP site. That can be a pretty big issue. I have a paper out on my website about de-anonymizing I2P that goes into this in a little bit more detail. Another example of application level issues would be Bittorrent. Now I'm basing most of this slide on the work of the people I have credited down at the bottom. I'm not going to butcher the poor people's names, but go check out their work. Essentially, Bittorrent has a whole lot of issues when it comes to using it over Tor and keeping it anonymous. You may want to look into I2P's solution for this, where it's a version of Bittorrent totally hosted inside the network. But a few of the issues, let's say if Tor is only being used for contacting the tracker, I could just watch the announce messages and extension protocol handshakes to extract real IPs at the exit point. Another issue is the people you're actually grabbing the files from, or you might be sending stuff to the tracker over Tor. Well, you're connecting directly to the people hosting the files, and those people are getting your IP address. Another issue again with Tor is if Tor is only being used for contacting the tracker and SSL is not used, I could change the return peers list to point to me as one of the sources and watch for that outside connection, and then try to correlate an IP based on the peer ID and the port. Like I said, there's a lot of things in the Bittorrent protocol that sort of allow people to more easily track who's who. Even if the peer traffic is sent over Tor, if the DHT is used, the IP may still be revealed because UDP packets are not sent over Tor. I can scrape that distributed hash table for trackerless torrents and try to correlate an IP based on that peer ID and port I mentioned before that I saw coming through my exit point. I may then be able to infer the sender and receiver of other non-BitTorrent traffic because of Tor's shared circuits. So if the same circuits is being used for BitTorrent traffic as for HTTP traffic, well, you need not de-anonymize the BitTorrent user, and if that same circuit is also sending HTTP traffic, well, you know who's sending that also. Kind of an issue there. Get another example that I wanted to mention was IRC, and I kind of stumbled across this accidentally when I was using the IRC client with I2P. I was noticing whenever I connected to IRC, I was able to right click and do a whois on my own name, and well, lo and behold, despite the fact that I was logged in as some dude, by default Pigeon and probably some other IRC clients for that matter were also including in my real username on the box I was on. Well, if you look around online for I2P and the name Adrian, it doesn't take too long to figure out who some dude might be. Now, to keep this from happening, at least in Pigeon, other IRC clients are going to vary. Go underneath Modify Account, Advanced, and set the username and real name that you want to use so that it doesn't default to just figuring out what account you're logged in as and sending that. After doing that, you'll see I have a slightly modified whois response, which is a whole lot more anonymous than what you saw a few seconds ago. There are a few general mitigations I'd like to point out when it comes to application flaws, although since things vary so much from application to application, I'm going to concentrate on browser issues and perhaps web apps. Client-wise, make sure your browser is set to send all traffic through the Darknet or none at all. You may want to look into setting firewall rules to make this happen, to where that box will only connect to anything via the Darknet connection. You want to limit the plugins you use. Not all plugins properly respect the proxy settings of your browser, and also does issues with vulnerabilities in plugins, Acrobat, that could lead someone to sending you, let's say, a compromised document. That document causes a problem on your box, and your box then contacts the original host over the public internet. That would be a big issue for your anonymity. You'll want to use a separate browser for all your Darknet activities. I keep a copy of the Tor browser bundle on my desktop and use it pretty much exclusively for all the activities I do on .onion and .i2p sites. Also, you may want to check your browser against sites like dcloak.net and Panopticlick. dcloak.net is from the Metasploit folks, and essentially what it does is it tries a bunch of different techniques to have your browser contacted outside of the proxy connection to try to find your real IP address. Panopticlick is a project to see how trackable people are from things besides just a cookie. For instance, the user agent string, the resolution of the machine, and so forth. These are both good sites to check out and to see how unique you are, or whether or not someone can quickly find your IP address. Though keep in mind they're not comprehensive necessarily. Now when it comes to hidden servers, a few things you'll definitely want to do is make sure your stuff's patched. If you happen to have a really old version of PHP BB running on your hidden service or EAP site, well, you're likely to get pwned, and if they pwn you in the right way, they can make that connection back outside of the Darknet to them over the public internet, look at it and figure out, oh, this is where the person's actually hosting that site. Also, don't run an EAP site or Tor hidden service on a box that routes to the public internet. For instance, a while back I was looking around at EAP sites, and I'd find that people were hosting EAP sites that also had an internet-facing IP address. So what I did was I'd sit there and harvest all the IP addresses I could find that belonged inside of I2P, and I'd query them for the vhost that I saw as an EAP site inside I2P. So let's say someplace.i2p. I'd basically go to each one IP address and go, okay, requesting the root document, and I'm setting my host header to someplace.i2p. If the page returned was the same, or mostly the same, on both the internet facing site as it was in the I2P facing site, well, I had a pretty good idea who was actually hosting that content. Next up are attacks on centralized resources, infrastructure attacks, and DOS attacks, which I put under one heading for the sake of this presentation. The attacks I'll be covering here are not so much against individual nodes, but the network in general. People come up with all sorts of categories. Things like starvation attacks, where a set of nodes might say they're going to offer certain resources and then not. Partitioning attacks, where various techniques are used to separate the Darknet into different sections, and then the attacker can search for a needle in a smaller haystack. And flooding, where essentially just tons and tons of traffic are sent in to disturb the network. Standard DDoS attacks against resources inside and outside the network if going through the network are likely to be soaked by other peers. First of all, I find DDoS to be a silly thing to do for a political statement. You hear various hacktivists talk about, yes, well, DDoSing, it's like a internet sit-in. Please, if you want to discuss it, we can discuss it outside of this talk. But it's kind of silliness. But regardless, occasionally people will mention the idea of, hey, let's do our DDoS through Tor. That way we can stay anonymous. Well, first of all, more than likely you'll be DDoSing Tor instead of the target that you're intending, thus disturbing the network for people who are trying to use it for more legitimate purposes. So please, just don't. Tor will take the blunt of most of your attack as opposed to your target anyway. Also, shared known infrastructure can be a huge problem. For example, directory servers. If the directory servers are taken out, well, certain darknets that function like Tor would have huge difficulties servicing people's requests, or more accurately, people would have a huge problem actually connecting into the routers that can service their requests. Also, total or at least severe blocking of the internet can cause huge issues for darknets. Now, a few incidents of DOS attacks against the infrastructure of some darknets. Go check out the Tor project blog. Back on September 25th, 2009, China blocked access to some of the core directory services of Tor, causing huge problems. This is one of the reasons why bridge routers are so useful, which I'll talk about here shortly. Another example might be the blocking of internet access in Egypt, Libya, and Iran. Obviously, you're not going to be able to get on these various networks like I2P and Tor if you can't even get an internet connection. To give you an example of a DOS of directory servers, well, when China did their thing, when people went to request, hey, what routers can I bounce my traffic through, and went to ask the Tor directory servers, well, they couldn't reach the Tor directory servers because those were blocked by the Great Firewall of China. They couldn't get the list, they couldn't route their information, unless, of course, they knew various bridge nodes. A few mitigations. Well, I've already mentioned bridge nodes a few times. Basically, a bridge node is like a standard router in Tor, except it's not announced by the directory servers. You either have to be told it by someone who set one up, or I think there's some email addresses you can email the Tor project at, and you'll get back a little list. And I think they also hand them out in a few other ways. But there's no central repository that a country can go in, get the entire list, and block it all. At least that's the core idea. I2P handles things a little bit differently. They have a distributed infrastructure where they use a distributed hash table to take care of routing and announcing what service is where. Now, it does have some central resources in the sense that if someone took out the dev site, it'd be harder for people to get the core packages to install I2P, but it's a slightly different issue. Generally speaking, because it's distributed infrastructure, as long as you get a few nodes that are in I2P and can connect to those, you'll slowly start to build up a list of other nodes you can connect to, and it would be hopefully self-maintaining. The distributed hash table I mentioned before is essentially a way of doing a distributed database across nodes in the network, and are supposed to, if designed properly, handle passing records off to other nodes, so that even if there's a certain amount of churn in the network, the data can still be there and accessible. Another mitigation I like to see people do more research into is protocol obfuscation. If someone can know that you're using a certain darknet protocol, well, they can try to block that protocol. Also, in some countries, even if they can't see what the traffic is, if they just know that you're using this particular protocol, that might be enough for someone to come knocking at your door. Tor handles this to some degree by trying to make most of their traffic look like HTTPS traffic. I2P chooses a random port on each installation and sends all the traffic encrypted, so hopefully it just looks like a big blob that's undecipherable, but someone still may ask questions. Total and severe blocking, however, will take a little bit more mitigation to get around, which I'll cover in the next slide. People have been coming up with ideas for doing mesh networks or store and forward networks. Essentially, a mesh network, you have a set of nodes that are in a sort of ad hoc mode where they can talk to each other and spontaneously organize routing, so that when something goes into the network, it can figure its way back out, and it's a good way of setting up ad hoc infrastructure. So if anybody out there has heard of the whole Internet in a Box project, that's something similar. However, if you're in certain areas, you're not going to be able to create a strong enough mesh where everybody can get their message out at all times. So you might have a system like a store and forward, where someone creates a message, and when they get within range of another node that can pass it on, it passes it on. When that one gets in the range of another node that can pass it on, it passes it on, and so on and so forth. I have a few resources for you if you're interested in doing more research on mesh networks. Unfortunately, there doesn't really seem to be a clear forerunner in setting up the layer 1 of such a Cipherspace system. Go check out the Wikipedia entry for links off the various mesh network projects that are out there. Also, check out the Btk project for some people who are trying to develop something similar to this. Also of interest might be the New York Times article that came out recently about the US underwriting an internet detour around sensors, sort of the internet in a suitcase. Clock-based attacks is another subject that has received some research. Some protocols allow you to check the remote system's clock. So clock differences can be an issue, especially when someone's trying to profile people using a darknet. If a clock difference is major, for instance if you're running a server and it's 5 minutes different from standard time, well, that's pretty useful information while profiling. But even minor clock issues may be useful when combined with statistical analysis. For examples of clock-based attacks, check out these articles. Stephen J. Murdoch wrote a paper called Hot or Not, Revealing Hidden Services by the Clock Skew, in which he showed on his own private Tor network that differences in CPU usage or location of a server can cause differences, of course, in temperature, and these differences in temperature will cause the internal clock to skew one way or the other. However, keep in mind when he did this research, he used his own private Tor network to do it, as the public Tor network has a whole lot of jitter and instability caused by other things, making doing statistical analysis attacks on it somewhat harder. Also of interest might be my I2P clock differences section in the article I wrote a while back on de-anonymizing I2P EAP sites. Part of my research into de-anonymizing I2P EAP sites was just profiling what time differences were out there between my local clock and the clock of both EAP sites, and also publicly facing IP addresses of known I2P nodes if they were running a web server. Essentially, I would just make a web request and take note of the time date stamp, log all this information, and try to correlate it later. This table shows some of the information I gathered while profiling EAP sites and web servers running on IP addresses that I knew were part of the I2P network. I then grouped them all by their clock difference from my own local clock. Now if it's only a few seconds, that didn't tell me a whole lot of information. It takes a certain amount of time for a message to go out my out tunnel and back in my in tunnel. So those minor few seconds difference are inconsequential. However, when a certain IP address and a certain EAP site were both about 4,500 seconds different from me, and they also both happen to share the same server header, that's a pretty good indication that they might be the same box. Since then, I2P has put in some mitigation so it strips out that server header tag. There are various mitigations for clock-based attacks. Some of them are rather inadvertent and inherent to the network. For instance, there's a certain amount of jitter in both I2P and Tor. It takes a little bit of time to send a request out and get back a response, and that amount of time is variable depending on the path you take, and you can't be sure whether or not that time difference is because the remote CPU's time difference is that great, or if it's just because of delays in the network. Setting your clock to a reliable NTP server, however, is probably a good idea, but it has to be a reliable one. If you set it to an NTP server that's consistently 5 minutes different, well, that's another point of profiling. Also, some Darknet clients have mitigations built into them. For instance, I2P does various things to try to keep its internal clock synchronized with other I2P hosts. However, this clock is internal to I2P. It doesn't necessarily affect the clock of an HTTP server running on the same box, so it only helps so much. The next attack I want to cover is metadata in files, and I find this one quite interesting. Metadata is data about data. There's all sorts of file formats that contain metadata. To name just a few, there's JPEGs with the EXIF data and IPTC data, PDFs with things like usernames in them, docx files, EXEs, XLS, XLSX files, PNGs, just to name a few. There's way too many to list them all. This kind of data you'd be able to pull out of these would be things along the lines of usernames and edits in the case of Office documents, GPS info in the case of some JPEGs, network paths in the case of some Office documents. In really old Office documents, we're talking really old, like Office 97, you were actually able to extract the MAC address of the box it was generated on. It all depends on the file format. While I don't know of anybody's identity that's been revealed inside of a darknet because of metadata, I can think of several people who have been pwned by metadata on the public internet. Kat Schwartz comes to mind. A while back, she took a sexy photograph of herself with her head held back smoking. She cropped it and posted it online. However, the tool she used to crop it didn't take care of the EXIF data, specifically the thumbnail that was embedded in the EXIF data. So if you went and looked at that data in the picture she posted, well, let's just say the thumbnail goes down a little bit further than the picture I have up in this slide. Another example is Dennis Rader, better known as the Btk Killer. He decided to start gloating to the cops again, and instead of doing it his old way, he decided to send a Word doc on a floppy to the police. Well, when they looked in the metadata of that Word doc, it happened to have the name of his church as well as last modified by Dennis in it. It only took so long for them to find him thereafter. One of my favorite examples is Nephew Chan. What he did was he posted some pics on 4chan of his semi-nude aunt, which he took with his iPhone. Well, anonymous being anonymous, pulls the EXIF data, and at that time, by default, the iPhone was putting in GPS information in that EXIF data. They saw it and they said, hey, why don't you post the rest of them? Or we'll tell your aunt what a perv you are. If you want more information on all that drama, go check out the archive.org archive of Encyclopedia Dramatica from quite a few years ago. Alright, mitigations for metadata. Well, obviously, clean it out. Unfortunately, this varies from app to app on how you do it, so it's not exactly something I can easily cover. The next category of attacks I want to talk about are local attacks. At this point, it's already pretty much a lost cause if someone has physical access to your box, but let's talk a little bit about them anyway. A quick overview. If someone has access to your box, well, you're sort of hosed. At this point, it comes down to just general forensics work. Data on the hard drive the person can find, like if someone saved images or other types of documents on the hard drive. Cache data and URLs if the person's not using private mode, although I guess privacy mode is of different levels of efficiency depending on which browser you're using. And then there's things like memory forensics. Let's say the person is using a live CD and hoping that's going to keep them anonymous. Well, if someone captures the machine quick enough and can get it before the person shuts the machine down and memory is cleared, there's various things they can do. Of course, the best mitigation for local attacks is just not to let your adversary have physical access to your box in the first place. Barring that, however, there are various anti-forensics techniques you can use, things like booting from a CD or USB drive, and I have a class video out on my website that covers a lot of these topics. However, Andrew Case has done some work in doing recovery from memory if someone's using a live CD or USB. They have to get to the box while the machine's still up and running with the CD or USB, but there is some possibilities there. Full hard drive encryption is also probably a good option you want to look into. The next attack I want to talk about is Sybil Attacks. Also, as I prefer to call it, sock puppetry. Now, how many of you have ever actually heard of a Sybil attack? I've been playing around with Darknets for quite a while, and the first time I ever heard of it was when I started looking at academic research on anonymizing networks. Essentially, a Sybil attack is kind of like a sock puppet. Apparently, it pulls its name from a book where a character has multiple personalities. So essentially, think of it this way. It's like a sock puppet account on a forum system where a person is a normal user account and they might have another account that agrees with them or is used to help influence the outcomes of things in the forum system. People do much the same thing when they're gaming Wikipedia. So essentially, it's one entity acting as more than one entity. This may allow for things like controlling of routing, elections, etc., etc., etc. And it can make many other attacks a lot easier. For instance, if you have a whole lot of nodes in the network, they're all acting as separate nodes, but they're controlled from one particular place, well, you can use those for things like traffic analysis, or possibly various partitioning attacks. Now here's a quick sock puppetry overview. Let's say you have a couple zombies out there acting as your sock puppets. You could do things like say, hey, if the Darknet is based on a random walk, come this way. Or if there's a certain election for who should be the core maintainer of information, well, you could possibly manipulate that as well. But if all of these are controlled by one central entity, we might have undue influence on the network and cause various problems. Another example might be first in chain, last in chain sort of problems, where if someone, let's say for example Tor, happens to control both the first point you talk to in passing your message in and the exit point, it makes it a whole lot easier to do traffic correlation attacks, which I'll be talking about here shortly. While there are no absolute fixes for Sybil attacks, there are various mitigations. One is to make it cost something to have nodes join the network, using some sort of proof-of-work algorithm like hash cache. If you are familiar with Bitcoin, it works along a similar principle. Another common mitigation is to use some sort of IP restriction when it comes to peering. Both Tor and I2P restrict peering between IPs on the same /16. This is done to keep a circuit or tunnel from using multiple nodes belonging to the same organization's IP network. Central infrastructure may also be more resilient to Sybil attacks, though it has issues of its own. Peering and profiling strategies to spot malicious nodes can also be of assistance. Then there's Sybil Limit, Sybil Guard, Sybil Infer, which use social network connections to decide peering and trust issues. I have my doubts about these solutions, however, especially after the whole Robin Sage affair. How many people would choose to friend someone even if they barely knew them? Now we're moving on to traffic analysis attacks, things like first and last in chain attacks, tagging attacks, timing attacks, but there's a lot of other sorts of ideas that fall into this category. There's a lot of focus in academia on traffic analysis attacks, but I imagine application layer flaws are more likely to snag someone. So many subtle variations on profiling traffic exist. It could be anything from timing of data exchanges, amount of traffic sent into and out of the network from various nodes, tagging of traffic by colluding pairs, and so forth. Generally, it takes a fairly powerful adversary with a good view of the network to pull off these sorts of traffic analysis attacks. But they're very hard to defeat in low latency networks, networks intended for protocols such as HTTP. When I first started looking into the I2P Darknet, I thought it would be incredibly difficult to pull off any sort of traffic analysis attack. And granted, the unidirectional tunnels do make it somewhat more difficult. However, while this is the logical view that we might have of the I2P network, with in-tunnels and out-tunnels and tons of different paths that data can take, your ISP's view, things might look more like this. Basically, they see stuff coming in and they see stuff going back out from you. This said, however, it would take the collusion of multiple ISPs, I imagine, to figure out who's exchanging data unless those people all happen to be with the same ISP. And even then, I think it's a little bit more non-trivial to figure it out. We're talking a lot of data being thrown left and right, and various network jitter and other issues can cause problems. One common traffic analysis attack is just to take note of where data is going in the network based on the amount of data. For instance, let's say a client sends in 5 megs of data and it goes out someplace else, and that someplace else might send 8 megs back through and it goes back to that original client. You might have a pretty good idea if you're an attacker that those two are communicating with each other. There's also more complicated timing attacks. For instance, the attacker could just sit there and watch timings that, like I mentioned before. They could try DOSing various nodes along the network to get closer to who's initially sending the data in. Basically, using this DOS attack, they can kind of put a timing tag on the traffic going through them or through other nodes that they're DOSing and see that pattern and hopefully try to correlate it. If the traffic is going through them, they can of course delay it themselves. This again would be very powerful in the first in, last out sort of attacks, first hop, last hop. Because if you're the first hop and you're delaying everything a certain amount of time, then not delaying it, then delaying a certain amount of time, you could possibly see that pattern at the exit point if we're talking about a network sort of flight tour. They could even try to change the load on the path to possibly figure out what nodes the message is going through. Now, a lot of these attacks aren't necessarily going to reveal the true identity of someone, but they could partition the network off to where, okay, I don't know for sure who it is, but I know this is the first hop, and then that just gets you a few steps closer to figuring out who's actually throwing the network traffic in there. There are various mitigations to traffic analysis attacks, one of the first being just having more routers. More routers means more potential paths, confusing an adversary trying to figure out who's talking to who. More covered traffic helps, so each node's communications become a smaller needle in a larger haystack. For example, even if you don't use I2P's customized Bittorrent, others using it and routing through you causes a great deal of covered traffic that helps confuse who is sending and receiving what on the network. Entry guards for the first hop can help mitigate the first and last in chain attack. If you were to choose a random path for your data every time, eventually you may choose a path where an adversary controls both the first and last hop. Tor implements it so you have a certain set of entry guards you always use as your first hop, so that you won't eventually randomly choose an adversary's path. Granted, you may have bad luck and end up with an adversary as an entry guard, but at least you have a chance. One-way tunnels can help so that the request and the response do not follow the same path. Short-lived tunnels may help, giving adversaries less time to collect statistical information on a connection. Better peer profiling may help spot potentially malicious nodes. Signing of data will help keep it from being modified in tagging attacks. I2P does this, though I don't know if it has mitigations in place to avoid tagging by changing the data delivery timings. Fixed speeds are also an option so that all the traffic looks very regular and featureless, though I don't know how practical this is for many applications. Padding and chaffing can be used. In this scheme, the message is occasionally padded to make it larger than the data that the user is actually trying to send. And occasionally this extra padding is dropped off as chaff. This makes analysis by traffic size more difficult, but at the cost of extra bandwidth being used. Non-trivial delays and batching can also be implemented, but this is more of an option for latency tolerant applications like email. Non-trivial delays and batching with web traffic would be pretty frustrating. That said, if a network handles both latency tolerant and low latency types of traffic, then both can benefit from the extra cover of using this system just for the latency tolerant apps. Next up are intersection and correlation attacks. Intersection attacks could be as simple as just noting who's up when a certain service can be accessed and who's down when the service can't be accessed. You might know the real IP address of a node that exists in the network, but not know if he's hosting anything or what he's sending out. However, if you know just that a hidden service goes down and that certain IP is no longer reachable at the same time, you might be able to figure out some information just from that. All sorts of techniques can be used to help reduce your search set. If you had to search every single node in the network to see whether that was up, well, that would be an issue. Application flaws and information leaks can also help you narrow down your anonymity set and figure out what particular subset of the network you actually have to search in for someone. You can help narrow down your anonymity set by doing various harvesting attacks where you grab more information from the network and start figuring out who's who and basically partition out how you're going to do your search. Let me give you an example. Let's say there's a Tor hidden service out there and you have a list of Tor nodes through various other means. You could try to contact the hidden server. I'm using ping in this little video, but a more accurate thing might be a quick HTTP request. Then you might go ahead and do a request to each one of the IPs as well in series and try to note which ones are up while the hidden service or EAP site is up and which ones are down when that particular EAP site or hidden service is down. Various techniques can be used to cut down on the number of boxes you need to check. While I was doing my I2P research, I did something similar to the following animation. First, I would check to see what server software an EAP site was running and note this by whatever it returned in the server header field. Since then, I2P has started stripping off the server header so that you don't have this information to go on. However, there might be other vectors that could be used by an adversary. After that, I'd harvest as many IPs as I could and find out who all was participating in I2P. I could do this fairly easily by essentially scraping the distributed hash table by looking at what entries I had on my local machine. Then I'd send a request to each one of those IP addresses to see if it had a web server listening on its public internet facing IP address. If it did, I would note what server header it returned. Then I'd look for correlations between the server header given to me via the IP address and via the EAP site, and if they matched, I'd make a vhost request for that virtual host of the EAP site. For instance, I request from the IP address, modify what host I was looking for and say, hey, are you running something.i2p? If it returned me the same page off the public facing IP address as it did from the EAP site, well, yippee, I've most likely found the true network host of that particular EAP site. There are various mitigations to help fight off intersection and correlation attacks. The first obvious one is just having more nodes. If a network is very small, it's pretty easy to figure out who's talking to who and who might be hosting something. However, the more nodes there are, it goes back to that whole analogy of being a needle in a much bigger haystack. Also, if the Darknet provides less information to an attacker, it becomes harder for them to reduce the anonymity set. When I mentioned that I2P started stripping out the server header whenever you set up an HTTP server type tunnel, well, this gives the attacker less information to be able to partition out the people they might want to attack. This makes scraping and harvesting more difficult. Another thing can be done depending on how the network is laid out. If the particular node that's doing the attack, if it's noticed that the person is requesting thousands of entries saying, okay, give me all the information on this node, information on this node, information on this node. Well, that's kind of suspicious behavior. So things could possibly be done to say, okay, there's only so many requests that this particular node can make at any one time. If you want more information on the work I was doing on I2P, go check out my de-anonymizing I2P paper and talk, which I'll link to in the next slide. Here are some links that should be useful to you for further research. First up, there's the selected papers in anonymity you can find out on Freehaven. Tons and tons of academic research are out here on various anonymizing networks. Also, check out the I2P threat models page and the links that come off of that page. It's an excellent resource that simply explains various attack methodologies. I have a more general talk on Darknets out on my website if you want to check it out. have multiple versions of it, but the most current one is the one I did at the AID Winter meeting earlier this year. Also, I have a paper and a video from Black Hat on de-anonymizing I2P EAP sites. Thanks to the conference organizers for having me, Tenacity for helping get me to DEF CON, my buddies from DerbyCon and ISD Podcast for the support, and the Open Icon Library for some of the images I used in the animations of this presentation. A few events I'd like to mention. If anybody gets a chance, please come out to DerbyCon. We're running from September 30th to October 2nd of this year. We hope to make it a yearly event. Also, there's the Louisville InfoSec, which happens just the day before, and here's a huge list of different conferences I like to attend. Make them if you get the chance. Finally, are there any questions? Thanks for your time.